Just give that a second now just to open up. So my apologies here, guys. Murphy's Law, if something can go wrong, it will go wrong. But SPSS seems to be opening up here. Brilliant. And what I'm going to do now is just hopefully we have our data set that we've been working on. Otherwise we just set it up again. It shouldn't take too long to do that. So I'll just give this a second here to boot in. I don't know what's happening with SPSS version 25 here. It seems to have. So here's my data set. I'm just going to reopen that up here. Okay, and I have my two. Let me just do my two variables again. So my first variable is dice outcome 1, and my second variable is dice roll outcome 2, and that's a scaled variable. I'm just going to get my data again from Excel. I'm going to Excel. I'm going to copy the first set of numbers. Let's say here's my first set of numbers. I'm going to copy them out there. I'm going to put them back into SPSS. There we go. And I'm going to copy my second set of data set, okay, which is the biased dice. Okay, copy them out there, and I'm going to go back into SPSS. I'm going to put them in here, and now what we're going to do is going to run that test. So I'm going to go to Analyze, the chi-squared goodness of fit test, as opposed to the chi-square test of independence. The goodness of fit test can be found under non-parametric tests, legacy dialogues, chi-squared. So I'm going to ask for that. The first variable I want to test is the dice roll. Well, let's just test the first variable, which is dice roll outcome 1. And what I'm saying is my expected values are all categories should be equal. Yeah, so everything should be as equally likely to happen as anything else. Where are we going to get the data range from? Well, just get it from the data itself, which are the numbers 1 through to 6. And I'm just going to hit OK on that. And what I get is I get some output here. Yeah. So the null hypothesis. So you can see here my observed frequencies. The values that actually occurred are 1, 2, 3, 4, 5, and 6. My observed frequencies are a face value of 1 occurred 4 times, a 2 occurred 10 times, a 3 occurred twice, and so on. The expected frequencies are all the same. Okay, and here's the result of my chi-squared goodness of fit test. Don't forget, the null hypothesis is that the data, the observed data, okay, follows the expected distribution. We've specified the expected distribution to be a distribution where everything is as equally likely to happen as anything else. We did that in our SPSS window. And you can see that my significance value, my p-value, is 0.156. So once again, if the p is low, the null must go. In this case, the p isn't low. So what this is telling us is that there's insufficient evidence to reject the null hypothesis. So there's no evidence to suggest that the observed distribution is different to the expected distribution. And that's what I suppose we would expect to happen, because we set that up that the outcomes of the die were all equally likely based off our first frequency distribution. Let's see about the second die outcome to see what happens here. Okay, so I'm going to go to Analyze, non-parametric, chi-squared, legacy dialogues chi-squared, and let's get rid of this here, and let's put in our second outcome, and let's compare that against a distribution, okay, where the expected values are all categories are equally likely. That's what I have specified here. We don't have to do that. We could compare this distribution, the observed distribution, against specific values and assign specific outcomes to those values. But let's just go with this under the null position, that everything is as equally likely as anything else, and let's hit OK on that. And then we get, well, our observed distribution is here. The values are 1, 2, 3, 4, 5, and 6. A 1 occurred twice, a 2 occurred 3 times, a 3 occurred twice, a 4 occurred 4 times, a 5 occurred 7 times, but the 6 occurred 12 times based off our probability distribution. We'd expect everything to happen 5 times, okay? So now we're comparing these observations, these observed frequencies against these expected frequencies, and here's the result of the chi-square test. Once again, the sig value is 0.01. So if we were to run this at the 5% significance level, you can clearly see that the p is low. If the p is low, the null must go. In this case, we compared the significance value against the alpha value for our test at 5%. Well, we have 0.01 is less than 5%, and hence we reject the null hypothesis. So what this is saying to us here is that there's evidence to suggest that the observed distribution, okay, is different to the expected distribution. Okay, in other words, the expected distribution is where the die is fair. The observed distribution is different. So the observed distribution, we would have confidence in saying, since we ran it at the 5% level of significance, we'd be 95% confident in saying that the die, or the dice that was used to generate these particular sequence of numbers, yeah, okay, these particular observed frequencies, that the die actually is not fair, it's unfair, it's biased, it's rigged, and we shouldn't be using that die in this particular casino, okay? Unless you know that it's going to give you 6 all the time or most of the time, and hence you might get a little bit of an advantage. Okay, guys. Once again, this was Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. And this quick test was a chi-squared goodness of fit test. The next video is going to have a look at what's known as a chi-squared test of independence. So once again, guys, I hope that this video was intuitive, and more importantly, I hope that was helpful for you. And thanks for watching. Okay, bye-bye.